Hello, we want to talk about some bonding theories. In this first video, we want to talk about valence bond theory, or VBT. And in it, our bonds are going to arise from the overlap of atomic orbitals. And so let's look at the simplest example that we can come up with, and that's diatomic molecular hydrogen. Remember, hydrogen has a ground state electronic configuration of 1s1. So if we start out with two hydrogens and start moving them close together, we can look at their potential energy in regards to their internuclear distance. It's just a fancy way of saying the distance between the nuclei. And so as they get closer and closer together, they're going to eventually overlap. That overlap of their atomic orbitals would give us a bond. And there's some sort of minimum on this energy curve. One of the driving forces in nature is to try to get to minimum energy, where there's a low point, a minimum, which is the optimum distance between the nuclei. That would be your internuclear distance. Now, as they get closer and closer together, we'd be going off in this direction. Now we're going to start seeing the repulsive forces of the nuclei. And so it doesn't want to go in that direction. And as we go in the other direction, we'll see less and less overlap, which would be less desirable. And so there's this optimum internuclear distance that corresponds to this energy minimum. And so this is H2 with the overlap of the two hydrogens. And that would be our Lewis structure. But this is our valence bond diagram showing the 1s orbitals overlapping with each other. The next example let's do is, let's do hydrogen fluoride. And we could do a Lewis structure that would look something like this. It's a linear molecule, because they're just two atoms, and all diatomic molecules are linear. Hydrogen, its ground state electronic configuration is 1s1. Fluorine, 1s2, 2s2, 2p5. And so what we care about, the overlap of the valence electrons, and the overlap of the atomic orbitals which bear those, or carry those, or house those valence electrons. So we're going to overlap the 1s orbital of hydrogen with one of the 2p orbitals, the 2p orbital that only has one electron in it. So if we did a box diagram for hydrogen, it's got the 7 valence electrons. There are 2 in the 2s, 3, 4, 5, 6, 7. So we're wanting to overlap that p orbital that only has one electron in it. And so here's my hydrogen, 1s, and here's my fluorine. Now remember, p orbitals have 2 lobes to them. And so we'll maybe call this our vertical p orbital. And that's a p orbital that's going in and out of the plane of the screen that you see before you. And then there's this other p orbital that's horizontal. And where they overlap, that would give us our bond. The next example let's do is that of methane. So carbon's group 4, 1s2, 2s2, 2p2, and our hydrogen's got that 1s1 electron. here's our Lewis structure. And so we got a tetrahedral electron geometry. We also got a tetrahedral molecular geometry. That's important to keep in mind. So here's our carbon. Maybe I should do the box diagram. There's 2s and a trio of 2p orbitals. So 1, 2, 3, 4. So there's a p orbital. And there's a p orbital. And there's a p orbital. Remember, they're all at 90-degree angles. They're right angles to one another. And so that's a 2p, that's a 2p, and that's a 2p orbital. So let's bring in our hydrogens. There's one hydrogen, and it can overlap, make a bond. There's another hydrogen that can overlap to make a bond. There's another hydrogen that can overlap to make a bond. And now we come to the uh-oh moment. Uh-oh, because we still got another hydrogen to go. But there's no more p orbitals available for any overlap. Remember, each lobe, it takes 2 lobes to make up a p orbital. And so we can't go putting any more hydrogens on here. So we don't have any more atomic orbitals left to overlap to make a bond with that 4th hydrogen. So that's one uh-oh. The other uh-oh is these bond angles would be 90 degrees if these p orbitals stayed the way they were. But we know they're not. They're tetrahedral. They're really 109.5 degrees. So valence bond theory is good for some really simple molecules, but now we got into this a little bit more complicated molecule. Not very complicated, it's only got 5 atoms in it, and it falls apart. And it's just so like we had to take Bohr's model of the atom and modify it by coming up with quantum mechanics. Valence bond helps out a little bit, but now we need to come up with another bonding theory that we're going to refer to as hybridization. And I will invite you to take a look at that video.